everyone! Today we're doing notes for 7.1, estimating mu when sigma is known. So some assumptions about the random variable x. We have a simple random sample of size n drawn from a population of x values. The value of sigma, the population standard deviation of x, is known. If the x distribution is normal, then our methods work for any sample size n. If x has an unknown distribution, then we require a sample size n is greater than or equal to 30. However, if the x distribution is distinctly skewed and definitely not mound shape, a sample of size 50 or even 100 or higher may be necessary. A point estimate. This is an estimate of the parameter using a single number. X bar is the point estimate for mu. Margin of error. When using x bar as the point estimate for mu, the margin of error is the magnitude of x bar minus mu. And it's the absolute value of that because the margin of error will be both positive and negative. Our critical value ZC. For a confidence level C, the critical value ZC is the number such that the area under the standard normal curve between negative ZC and ZC equals C. So here are some levels of confidence and their corresponding critical values. We see for 70%, it's 1.04. 75%, it's 1.15. For 80%, I'm going to show you how we find these values. So for 80%, we know that the middle 80%, so if I want to fill this in, my middle 80% here is the size that we're looking for. So there's 20 left over. We divide that by 2, so we know there's 10% on either side. That way it's symmetric to the normal curve. So we can do our inverse norm, and we're going to do 0.10, comma 0, comma 1. Our mean is 0, standard deviation is 1. And so this is going to give us negative 1.28, which means this is negative 1.28, and this one is positive 1.28 for the z values. So I'll fill in 1.28. For 85%, it's 1.44. Let's do 90% together. So 90%, we're getting closer here to filling our area under that curve. So here's 90%. Again, there's 10 left over, divided by 2. We know we have 5% on each side. So we can do inverse norm, 0.05, mean is 0, standard deviation is 1. And this gives us negative 1.645. So then this side is positive 1.645. And I'll label that in our chart. I would like you to find the z value for 95% now. Okay, so for 95%, we have 5 left over. We're dividing by 2, so we have 2.5% on either side. So inverse norm, 0.02501, and this gives us negative 1.96. So I'll label this as 1.96 for that critical value. And our last one is 99%. So we're talking everything here under the curve. That's 99%, meaning we have 1% left over divided by 2. We're at 0.5% on each side. Whoops. So we can do inverse norm, 0.005, comma 01. And this gives us negative 2.58. So here we're negative 2.58, positive 2.58, and so that critical value is 2.58. Okay, the maximal margin of error. The formula for this, E is equal to ZC, so that critical value C, times sigma divided by the square root of n. So when the sampling distribution for X bar is exactly normal with mean mu, standard deviation sigma divided by root n, this occurs whenever the X distribution is normal with a mean mu and standard deviation sigma. The confidence interval for mu when sigma is known. This is the interval computed from sample data in such a way that C is the probability of generating an interval containing the actual value of mu. In other words, C is the proportion of confidence intervals based on random samples of size n that actually contain mu. Okay, so both of these formulas are important. Again, this is the one for the margin of error, and then our confidence interval formula is right here. In general, a confidence interval is your point estimate plus or minus the margin of error, which means you're going to have a statistic. In this case, it's X bar. We'll get to some where we're using P. Plus or minus our critical value. Well, the critical value is that ZC times the standard deviation of the statistic. That's our sigma divided by root n. All right, so here's our example. Julia enjoys jogging. She's been jogging over a period of several years, during which time her physical condition has remained consistently good. Usually she jogs 2 miles per day. The standard deviation of her times is sigma equals 1.80 minutes. During the past year, Julia has recorded her times to run 2 miles. She has a random sample of 90 of these times. For these 90 times, the mean was X bar equals 15.60 minutes. Let mu be the mean jogging time for the entire distribution of Julia's 2-mile running times taken over the past year. Find a 0.95 or 95% confidence interval for mu. All right, so our sample size is 90, which is greater than or equal to 30. So we know it's approximately normal. And our important information, X bar is 15.60. Our sigma is 1.80. And then our ZC, if we look back, we're looking for Z of 0.95. And this is 1.96. So our confidence interval formula, X bar plus or minus ZC times sigma divided by root n. We have 15.60 plus or minus 1.96 times 1.80 divided by root 90. So this gives us 15.60 plus or minus 0.37. So to get the lower bound, I do 15.60 minus 0.37, which gives me 15.23. To get the upper bound, I do 15.60 plus 0.37, which is 15.97. And this is my confidence interval. So here's some ways we can interpret confidence intervals. Since X bar is a random variable, the endpoints X bar plus or minus E are also random variables. We have a C chance of obtaining a sample such that the interval, once it's computed, will contain the parameter mu. After the confidence interval is numerically fixed for a specific sample, it either does or does not contain mu. So the probability is 1 or 0 that the interval, when it's fixed, will contain mu. If we draw many random samples of size n and get lots of confidence intervals, then the proportion of all intervals that will turn out to contain the mean mu is C. Once we have a specific confidence interval for mu, such as 3 to 5, all we can say is that we are C% confident that we have one of the intervals that actually contains mu. Another appropriate statement is that at the C confidence level, our interval is one that contains mu. If we take all possible samples of size n from a population and compute a C confidence interval from each sample, then C% of all such confidence intervals will actually contain the population parameter in question. Similarly, 1 minus C% of the confidence intervals will not contain the parameter. All right, so here's what this looks like. Let's say we have a population that's normally distributed. We take one sample of size n and find the mean of the sample. This X bar becomes the center of the interval. Then we do a bit of math to figure out the margin of error. This determines the width of the interval. Sometimes our interval captures the true mean, sometimes it doesn't. So again, we're taking x bar plus or minus the margin of error, or the full formula x bar plus or minus, remember margin of error is ZC times our sigma divided by root n. Okay, so in this picture here, the question says, how many of the intervals shown above captured the true population parameter? What percent of the intervals constructed is this? So here you can see this is mu. This is our population mean. And so if we're looking at each of these intervals, I'll label it on the bottom one. This right here represents our lower bound for each of them, the left arrow. The right arrow, this represents the upper bound. So that's like what we just calculated, those two values. The point in the middle, that's our point estimate or our x bar. Okay, so again, the lower bound, remember this is x bar minus the margin of error. The upper bound is our x bar plus our margin of error for each of these. So if I'm looking here, it says how many of the intervals shown above capture the true population parameter? Well, the true population parameter we can see is mu right here. And so any one that contains this value, we can count as one that has the population mean mu. So if we look carefully, there is one right here that does not capture mu. Right? It does not go over that population mean. So if I'm answering our question here, 24 out of the 25 capture the true population mean mu. Okay, 24 out of 25, that is 96%. All right, so Walter usually meets Julia at the track. He prefers to jog 3 miles. From long experience, he knows that sigma equals 2.4 minutes for his jogging times. For a random sample of 90 jogging sessions, the mean time was x bar equals 22.5 minutes. Let mu be the mean jogging time for the entire distribution of Walter's 3-mile running times over the past several years. Find a 99% confidence interval for mu. So check requirements. Is the x bar distribution approximately normal? Well, that we can say yes. Our n is 90, which is greater than or equal to 30. So approximately normal. Do we know sigma? Yes, our sigma is 2.40. What is the value of Z99? That is 2.58. What is the value of E? Remember, our formula for the margin of error is ZC times sigma divided by root n. Please find this. So we have 2.58 times, we have 2.40 divided by root 90. That's going to give us 0.65. What are the endpoints for a 99% confidence interval for mu? So our endpoints are x bar plus or minus the margin of error. Please find this. Okay, so we have 2250 plus or minus 0.65, which will give us 21.85 to 23.15. So explain what the confidence interval tells us. So the way we would interpret this, we would say we are 99% confident that the interval from 21.85 minutes to 23.15 minutes captures Walter's true mean running time for 3 miles. Now you can use this statement. Basically, you can interchange this 99% confident. You'll interchange that with whatever level of confidence you have. Then we have the interval from 21.85 minutes to 23.15 minutes. Again, you'll replace that with the value. Captures Walter's true mean running time. You'll put whatever the scenario is in here, okay? So again, you can use this statement and basically just interchange these values for the specific problem that you're looking at. Last, this is how you will perform and find the Z interval on the calculator. So we can read the directions here. It's under the stat menu. We're doing a Z interval, and we'll go over that in detail in class. Sample size for estimating the mean mu when sigma is known. So we have this formula, n equals ZC times sigma divided by E, and that is squared. This is where E is the margin of error, sigma is the population standard deviation, and ZC is the appropriate critical value. If n is not a whole number, increase n to the next highest whole number, so you always round up. N is the minimal sample size for a specified confidence level and a maximal error of estimate E. So a wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. A preliminary study of a random sample of 50 salmon showed S equals 2.15 pounds. How large a sample should be taken to be 99% confident that the sample mean X bar is within 0.2 pounds of the true mean weight mu? So N equals, we have ZC times sigma divided by E squared. So our Z of 99 is 2.58. Our sigma is approximated by the S, which they tell us is 2.15, and our margin of error is 0.2. So N equals, we have 2.58 times 2.15 divided by 0.2, and then we're going to square that. That comes out to 769.23, always round up, so this would be 770 salmon. And that's where we're going to end today.